In this video, we're going to go over solubility equilibrium, first the definition of it, and then how to solve an actual problem. All right, so what is solubility equilibria, KSP? Well, as the information on this slide says, it's when you take a solid and it breaks down into our ion. So we have silver chloride, breaking down the silver and chloride. Now, the thing about KSP is that their equilibrium constant is very small, much less than 1. And if you remember, for equilibrium, it is always the concentration of products divided by the concentration of reactants. And so since K is very small, what this means is that you mostly have reactants at the end of this reaction. And so you won't actually make much products. And these types of problems often deal with molar solubility. That is, what is the actual concentration that will dissolve? Now, if we look in the actual KSP for the silver chloride of breaking down versus the K I wrote, you notice we actually don't have reactants in the KSP. So our K is actually just the concentration of products. And why don't we have our reactants in our KSP? Remember, generally, we do not have solids or liquids in our equilibrium constants because their concentrations don't change during a reaction. So we just kind of assume that they're constant. I'll link a video to equilibrium constants below in case you need a little brush up on that. But let's get into our example problem. So let me erase my annotations here. Use the given molar solubilities in pure water to calculate KSP. So magnesium fluoride has a molar solubility of 2.65 times 10 to the minus 4. All right, so the first thing we want to do in any chemistry problem is write down the reaction. MgF2 solid goes to Mg2 plus aqueous plus 2F minus aqueous. All right, so some things to note here. How did I know MgF2 was a solid? One is because the problem told me KSP, solubility product. That's what SP stands for. So that is telling me, oh, the thing I start with is a solid. My other key there is molar solubility. Whenever you're given a molar solubility or you're asked to calculate molar solubility, again, that is just the problem telling you, you start with a solid, you're breaking it down to aqueous. So the next thing you might be asking yourself is, how do I know it's 2-fluorine, 2F minus? So fluorine is a halogen, and all halogens, when they're in water, will always be by themselves. So if it's F2, I3, Br4, whatever, you take the number and you just throw it in front of the molecule. So it's 2F, not F2. That actually matters quite a bit. The next thing we should do is write out our KSP expression. It is products over reactants. So Mg2 plus over F minus squared. Remember, we don't actually have MgF2 because that's a solid, so it's non-equilibrium. And for the 2F minus, this 2, or any number in a reaction, any stoichiometry coefficient, becomes an exponent in the K expression. Right. So now we have to solve for molar solubility. That is, how much do these actually dissolve? So we need an ice table for this. And if you're not sure how to use an ice table, I will link to problems below, or an example below, an example problem below that will tell us how to do it. First off, we only care about molecules that are in our KSP expression when it comes to ice tables. MgF2 is not there. So I actually ignore it. So if it's not in our KSP expression, I ignore it in the ice table. So how much magnesium and fluoride do I start with? Both of those are 0. Because remember, I'm starting with a solid and I'm going to drop it into water. So at the very beginning of the reaction, I haven't made any products yet. How much products am I going to make? Well, that's plus x and plus 2x. So remember, for stoichiometry in an ice table, when you get to the change column, that number should go with your x. And then I plus C equals E. So at equilibrium, the concentration of magnesium is X. The concentration of 2-fluorine is X. Now that we have equilibrium, we just plug that back into our KSP. So KSP equals X, which is magnesium, multiplied by 2X squared for fluorine. So KSP equals X times 4X squared. 2X squared is 4X squared, right? And then KSP equals 4X cubed. X squared times X is X to the power of 3. We actually know what KSP is. So 2.65 times 10 to the minus 4 equals 4x cubed. Divide each side by 4 because I'm solving for x. Let me get out my calculator to do that calculation. So we have 2.65 times 10 to the minus 4 divided by 4. So that is, whoops, sorry about that. Hit the wrong button. 0.0000663. 0.0000663. Your calculator might give you scientific notation as well. So to do this in scientific notation, so 1, 2, 3, 4, 5. It is 6.63 times 10 to the minus 5 is equal to x cubed. So the way to get rid of a 3 is that you cube root everything. And if you don't know how to do that on your calculator, you raise everything to the power of 1/3. That is the same thing as doing a cubed root. I know for me, doing anything that's not a square root, I always found that hard to find on my calculator, especially during a test. So that is the fast way to do it. Just do it raised to the power of 1 divided by 3. So I'm going to take my number that I just found and raise it to the power of 1 divided by 3. And x then, our molar solubility is 0.0405 molar. So that's all it is. You're just trying to find, what is the concentration that dissolves. So as a short little recap to this problem, first thing we did was write out the actual chemical equation. From there, we wrote out our KSP expression. Remember, any stoichiometry coefficients need to become exponents. We then wrote out our ice table. Again, same thing here, 2x for F minus because it's 2F minus. Then we just solve for x, and that's all there is to it. If you have any questions, please let me know in the comments below. Otherwise, I will see you in the next video.